And today we're going to review exponents and logarithms. See how well you remember everything about exponents and logarithms. So first of all, graphing wise, you have your exponential graphs. Some characteristics of exponential graphs is they have an asymptote and y equals 0. Whenever you plug in 0 for the exponent of x, you get 1, so that's a common point. And sometimes they're increasing if your value is bigger than 1, like in the 2. And sometimes they're decreasing if your value is between 0 and 1, like 3/5. You can always make a table of values if you don't remember how to graph something. It's a very, very powerful thing that you should never forget. You're stuck? Just put in a bunch of values. You can actually get a really accurate graph by just putting in more and more and more values. It's time consuming though. So our strategy is, I know what an exponential graph looks like. I can plot a couple key points. Like I would probably do 0, 1, and it's really easy to plug in 1 for x, 1, 4. Have my asymptote. So some things won't show up on a table of values, like you never get an asymptote showing up on the table of values. You just start to see it once you do more and more numbers. Same thing with the next graph. You could do a table of values for 1/3. Is that too quick? Or is that okay? You can plug in -1. You might also have this point would be a really easy one to plug in. 1, 1/3. And then you could do all of your transformations with exponential graphs as well. You want to try the next one on your own? The negative x there and the -3. I'll give you the choice. You can try it on your own, or you can and then once you've got an answer, you can take a look. Did it match up with what I've got up on the board? And something you may have seen before, may not have, it's not a big deal, is just describing, here I've got a mapping rule describing what's happening. What's going to happen to my x's? The only thing horizontal is you're multiplying by -1. So does that make sense that your x's are all going to change to -x? What's going to happen to your y values? The only thing that happens is you go down by 3. So what's going to happen to my y? It's going to go down by 3. And I wrote that out as a mapping rule. And then I could look at my table of values for my original 2 to the x graph and apply the mapping rule to each of them. So what happens to 0, 1? X gets multiplied by a negative. Y, you subtract 3, becomes 0, -2.
I'm gonna go home.
All right, I'll put up the answer. If you're not done yet, you take a look when you're done. And things that you'll check when you're done, do you have the asymptote in the right place? Do you have a couple of points labeled? And is the shape of your graph go towards your asymptote? All right. So our log laws that were on your formula sheet in grade 12, which means you now have to have them memorized for calculus. Do we remember them? Okay, well then that's good that we'll review it. So log law number 1, if you are multiplying inside the logarithm, that is the same as adding those two logarithms together. It is connected to an exponent law that says if you multiply powers with the same base, you add the exponents. So there's a connection with both exponents and logarithms that multiplying is added. Dividing is connected as subtraction. So if you're dividing inside of a logarithm, you can subtract the two logs. If you are dividing two powers, you subtract the exponents. The power log law. If you have a power inside of a logarithm, that exponent can come out and multiply in front. It's connected to the exponent law that if you have a power to a power, then you multiply the two exponents together. And then we have the change of base theorem. That if you have something you don't like, so for example, I will pick log base 3 of 7. If you have the newest version of the graphing calculator, you can type that into your graphing calculator. Remember where to find the log button, and you can type in log 3 of 7. If you have an older version, it doesn't let you put the 3 in. So then, you would use this formula, and the interesting thing about this formula is that the b only appears on one side. So when using this formula, if you have the left-hand side, you have free reign to choose whatever you want for b. And of course, if you have an older calculator, you would probably use 10 and do log of 7 divided by log of 3, because this you could type into your calculator. Or natural log, because you have that button as well, with a base of e. So anytime you have a base you don't want to deal with, it, you can change the base. And same thing, if you have a log divided by a log, you can change it back to a single logarithm. I want you to notice the difference between this log divided by a log and this, where the dividing is inside the logarithm. Okay? Sometimes it gets confused and someone will go, oh, can I do log 7 minus log 3? No. Because this log law works if you're dividing inside the logarithm. And this log law works if you have a log divided by a log. Remember these exponent laws? Anything to the 0 is 1. And negative exponents means that you could write it as 1 over. Basically, anytime you have a negative exponent, think of as a fraction, it flips to the other side of the fraction. So if your negative exponent was in your denominator, it can move up to your numerator. So if I had something with a bunch of things, A, B, C, D, I'll skip E so you don't think it's a number, F, and I had exponents, this one has a -2, this one has a 3, this one has a -4, this one has a -7, and this one has an 8. I can switch things around so that all the exponents are positive. So wherever things were positive, like the B cubed and the F to the 8, they would stay where they are because they're already positive. But the A squared could move down here, and the C to the 4 could move down there, and the D to the -7 could move up there, and change all your exponents to positive. We will be using positive and negative exponent rules a lot. When x is in the exponent and you're solving, you learned 2 methods in grade 12. One method used logarithms, and the other method was the non-calculator method that just used bases if you could make the bases the same. You can use that method if, like, the base here is 4, and the base here is 32. If both of those are powers with the same base, then we don't need a calculator. So for example, 4 is 2 squared, and 32 is 2 to the 5. If you can get the bases the same, then you can use your exponent rules to simplify. So here the exponent to an exponent means I would multiply and distribute. And then since the bases are the same, does it make sense that the whatever's in the exponents part would also have to be the same? So the -4 plus 6 would have to equal the 5x plus 20. And then solving for x from here. Is just basic combining like terms and getting x by itself. Next one has the same base of e. Try that one on your own. let's see how you did it. Use your exponent laws to try to get a single base on each side. And then once you've got a single base on each side, then we can make the exponents equal to each other. And factor and solve. Two answers for this one. X equals -3 and x equals 1. Now, if we can't get the bases the same, that's when we need to use our logarithms and our log laws to solve. So we'll do one. I mean, you can start the bottom ones on your own already if you want. I'm going to do one with you, and then I'm going to get you to try the second one on your own. Although the second one you can, yeah, you can't because of that 5. All right, so a review of solving using logarithms. This is the method that I like to use because it's systematic and it works all the time. So you're solving for x in a logarithm in the exponent. Can't get the bases the same, so you take the log of both sides. And it doesn't matter if you take log or natural log. You'll start finding that once you go to calculus further on in university, the log just disappears and they just use natural log after a certain time. It just happens more often. Then we want to solve for x, and the x is in the exponents. We use our log laws to try to pull that exponent out in front. And in this case, we can pull out the 3x minus 4 all out in front because it's the exponent to the whole thing, and that's one of your log laws. Log of 9 is a number, so we can distribute that log of 9. So I get 3x log 9 minus 4 log 9 equals log 25. I want to get the x by itself, so I'll get the term with the x on one side. Finally, I'll divide. And one of the things that's really nice about getting your answer with your calculator here is once you get your answer, you can plug it right back into the original equation. If it works, you know you got it right. Now what's on the left is what I like. There are other methods, and sometimes they're shorter, but they don't always work, so sometimes they're problematic. But if you wanted to in this question, I have 9 to the power of 3x minus 4 equals 25. I could change this to log form and write it as log base 9 of 25 equals 3x minus 4. Again, this is only going to be nice if you have that newer version of the calculator that lets you do this. Or you have to change that to log 25 divided by log 9 with your change of base. But now it's not hard to get the x by itself, and I get the exact same answer. This seems shorter. It's kind of nice. But it only works in certain situations, so that makes it a little bit problematic. I like the left-hand side because that strategy will work in all situations. But I do like thinking of shortcuts. So that other way is nice, and it doesn't work in the next example, but it was nice in this one. Oh, I can make it work in the next example if I get creative. I'll put up the answer. You can check your steps along the way. You're wanting to solve for x. In this question, something that is different than the first question, we have x on both sides. So in this situation where you have x on both sides, again, those x's are in the exponent. The whole purpose of using logarithms is to pull the x out of the exponent. Okay? And we have a log law which says if you take log of something, you have an exponent, that exponent can come out in front. So right here, this can come out in front. However, an easy mistake to make on the left-hand side is wanting to pull this exponent here. I'll circle it in red. If I pull this out in front right away, I've made a mistake. Because the log law says we can pull that exponent out only when it's the only power inside the logarithm. As soon as I have that multiplied by 5 right here, I'm not allowed to bring out that x plus 2 in front. So some of you, when you tried it on your own, you might have done that. Okay? Instead, I have to first use on the left the log law that says that multiplying is adding. Multiplying inside of a logarithm is adding. And then I'm allowed to, at this stage, bring that x plus 2 out. And when I did, I distributed right away. You can show the extra step of putting out in front in brackets and then distributing afterwards. I just distributed right away there. Okay. Now, you've succeeded at this step of getting the x out of the exponent. Okay? That doesn't look like an easy equation. It's got a lot of things going on. But now, here are my x's. There's an x there, and there's an x there. I want to solve for x. So I'm going to get all my x's, because they're like terms, on one side. I'll get all the other stuff that are just numbers, even though they're complicated looking numbers, on the other side. And then once I have both of those x's like that, technically I could show another step where I factor that x out, and then it's x times something. I just factored it out and divided right away. So a little bit of a breakdown of that one, of some of the things that you would see in those logarithms. And that's exponential equations. We also had log equations, where the x was inside of a logarithm. So one of the key things in a log equation is the ability to take something that's in exponential form with a base and exponent and change it to its logarithmic form with a base and an exponent. One thing I always remember is logs solve for exponents, so the thing that's beside and all by itself in the log form is the exponent in your exponential form. So how do we solve a logarithmic equation? Well, we move all the terms with logarithms on one side and all the terms that don't have logarithms on the other side, so that we can use our log laws to get a simple single logarithm. Once you have a simple single logarithm, you can take the log form, change it back into exponential form, and it will be easy to solve from there. Sometimes, though, using this process might give us an answer that actually doesn't work. So in solving logarithmic equations, at the very end, you always have to check to make sure your answer works, because sometimes you'll get something in your argument that's negative or 0, and you can't take the logarithm of a negative number, you can't take the logarithm of 0. So if that is the case, then the answer that you got is actually not an answer and an extraneous root. So let's do a couple. This is already a single, simple logarithm. So we can take this, and if I want to solve for this, step 1, I change it to exponential form. The base is 2, same base. Log solve for exponents, so the 4 over here is your exponent, and it's going to equal 2x minus 4. And from here, it's grade 9 math. It's not hard to get x by itself. I'm going to add a check mark here underneath, because once I'm done, I'm going to plug that 10 back in, just to make sure I'm not putting a negative number inside of a logarithm. Right? And 2 times 10 is 20, minus 4 is 16. Perfect. It's a positive number, so that is a possibility. Second one. Solving for x in a logarithm, but this time the x is the base. Change to exponential form. My base is x, my exponent is 4 is equal to 16. And I'd have to take the 4th root of both sides. Taking a 4th root is like taking a square root. You have to do the plus or minus. But when I check the plus value, it's good. The minus value, not good. I'm going to show you 2 methods for this one. We've got natural logs. So according to our steps that we wrote out at the beginning, the standard way of solving a question like this is move all your logarithms to one side, move all your numbers to the other side. We don't have any numbers, so the one side is going to be 0 in this case. And then I want to use my log laws to get things as a single logarithm. So the first thing I did is I noticed the 2 out in front, I could put in as an exponent. That's important to do because in order to use my log law for dividing, it only works when it's a log minus a log. You can't use that dividing log law if it's 3 logs minus 4 logs. It only works if it's 1 log minus 1 log. So I had to first put that 2 in as an exponent, so I have 1 natural log minus another natural log, and then I can divide. Once you've got a simple single logarithm, we can now change it to exponential form. So in this case, the base would have been e, the exponent is 0, it's equal to this, and once you change e to the 0 to 1, this becomes like a grade 9 question again. 25 is equal to x squared. You would get plus or minus 5, but when plugging in minus 5, you would have a negative inside of a logarithm. So we'd write that as an extraneous root. But this one is good. This on the left, this is your standard method. Standard method always works. Sometimes there's shortcuts, which are nice, but shortcuts don't always work. There is a shortcut when you have logarithms on either side. If you make a single logarithm on the left and a single logarithm on the right, would it make sense that what's in the green circles would have to be the same? And so you can sort of skip a bunch of steps and go right away to, I know that x squared has to equal 25. Same thing, solve it plus or minus 5 and cancel it to minus 5. That's a little bit short. This shortcut only works if you can write a single logarithm on one side and a single logarithm on the other side. If I change this question by saying, I'd like to add a plus 1 there, no shortcuts are possible.
Please excuse the interruption.
So,
Keith Carter to the office, please. Keith Carter to the office.
I really like that shortcut, but you have to realize that when you're doing things like that, they don't always work. So it's good to have the regular method as well available. Okay, I'd like you to try D and E. Put up the answer to this first one, see how you did. Sometimes find the log equations easier to solve than the exponential equation. It just seems it's not as busy. The 7 doesn't work though. Right, you plug the 7 in, you'll get a negative number. And then the last one. Everybody good on this one before I switch? Everybody not quite? Okay, I'll wait a second. And then the last one. Again, we'll put our logs on the same side first, and then we're adding so we can multiply. I distributed that negative x right away. Change it to exponential form. 2 to the 3 is 8. Factor and solve, and 4 doesn't work, but minus 2 does. Kind of crazy. So be careful, because sometimes you see a minus answer and think the minus answer is wrong. That's not the case. You always have to plug them back into the original and see if the original caused you to have a negative log. A log inside of a negative inside of a logarithm. So if you want, you can start the next two. I think you're able to do the last two examples. You can try them on your own. I'll put up the answer right away for the next one. If you want to find an x-intercept, that means you're plugging in 0 for the y, and then it's again, get your logs on one side. So take a look, try it on your own if you'd like. I have the answer up here. And I'll put the answer to the last one up in a bit. Mr. LaFrance's class had a fire drill this morning, so I think we successfully got ahead of them. Yes. That's going to be good because then, you know, when we let them get time to catch up, we can have some time to work on take-home quizzes in class or something like that, which I think you'd like. And again, you'll notice at the end of the page, if you're like, ooh, Today I realized I need to practice logarithms more. If you want more questions, the textbook has questions there you can look at and work on. I'll put up the answer to the last one at the beginning of class tomorrow, but I'll put it on here for the video so that it's all on this video as well. And then I'll go, yeah, I'll do that at the end, so if you're still working on this one, you can. So here is the answer for the last one, just so that it's on the video. I'll put the previous one back up if you weren't quite finished, so you can check this later.